In this video, we are going to learn about differentiated spectroscopy. First, let's learn about the ultraviolet spectroscopy. So, before moving on to the details, let's learn about introduction to ultraviolet visible spectroscopy or UV spectroscopy. Absorption of ultraviolet and visible radiation. Absorption of visible and ultraviolet radiation is associated with excitation of electrons in both atoms and molecules from lower to higher energy levels. Since the energy levels of matter are quantized, only light with a precise amount of energy can cause transitions from one level to another level will be absorbed. The possible electric transition that light might cause are antibonding, and bonding along with another bonding. So in each possible case, an electron is excited from a full low energy ground state orbital to an empty higher energy excited state antibonding orbital. Each wavelength of light has a particular energy associated with it, and that particular amount of energy is just right for making one of these electronic transitions. Then that wavelength will be absorbed. The larger the gap between the energy levels, greater the energy required to promote the electron to the higher energy level. The larger the gap between the energy level, the greater the energy required to promote the electron to the higher energy level, resulting in light of higher frequency and therefore shorter wavelength being absorbed. All molecules will undergo electronic excitation following absorption of light, but for most molecules, very high energy radiation in the vacuum ultraviolet is required. Consequently, absorption of light in the UV visible region will only result in the following transitions. Therefore, in order to absorb light in the region from 200 to 800 nanometer, where spectra are measured, the molecules must contain either carbon bonds or atoms with non-bonding orbitals. A non-bonding orbital is a lone pair and say oxygen, nitrogen or a halogen. Pi bonds are formed by sideways overlap of half-filled orbits on the two carbon atoms of the double bond. The two red-shaped shows in the diagram show ethane as part of some pi bonding orbital. Both of the electrons are found in the resulting pi bonding orbital in the ground state. Always overlap of a half-filled pi orbitals. Molecules that contain conjugated systems alternating single and double bonds will have their electrons delocalized due to overlap of the pi orbitals on the double bonds. And benzene is a well-known example of a conjugated system. The Kekulé structure of benzene consists of alternating single double bonds and thus give rise to the delocalized system above and below the plane of carbon-carbon single bonds. As the amount of delocalization in the molecule increases, the energy gap between the pi bonding orbitals and pi antibonding orbitals gets smaller, and therefore light of lower energy and longer wavelength is absorbed. Although beta-1,3-diene absorbs light of a longer wavelength than ethane, it is still absorbing in the UV region and hence both compounds are colorless. However, if the delocalization is extended further, the wavelength absorbed will eventually belong enough to be in the visible spectrum of the visible region of the spectrum, resulting in a highly colored compound. A good example of this is the orange plant pigment beta-carotene, which has 11 carbon-carbon double bonds conjugated together. Although the beta-1,3-diene absorbs light of longer wavelength than ethane, it is still absorbing in the UV region and hence both compounds are colorless. However, if the delocalization is extended further, the wavelength absorbed will eventually be long enough to be in the visible region of the spectrum, resulting in a highly colored compound. A good example of this is the orange plant pigment beta-carotene, which has 11 carbon atom double bond conjugated together. Beta-carotene absorbs throughout the UV region, but particularly stronger in the visible region between 400 and 500 nanometer with a peak at 470 nanometer. Groups in a molecule which consist of alternating single and double bonds conjugation and absorb visible light are known as chromophores. Transition metal complexes are also highly colored, which is due to the spilling of the d orbitals when the ligands approach and bond to the central metal ion. Some of the d orbitals gain energy and some lose energy. The amount of splitting depends on the central metal ion and ligands. The difference in energy between the new levels affect how much energy will be absorbed when an electron is promoted to a higher level. The amount of energy will govern the color of light which will be absorbed. For example, in the octahedral copper complex, yellow light has sufficient energy to promote the electrons in the lower energy level of the higher one. It is possible to predict which wavelength is likely to be absorbed by a colored substance. When white light passes through or reflected by a colored substance, a characteristic portion of the mixed wavelengths is absorbed. The remaining light will then assume the complementary colors to the wavelengths absorbed. This relationship is demonstrated by the color wheel shown on the right. Complementary colors are diametrically opposite to each other. So, UV visible spectrometers can be used to measure the absorbance of ultraviolet or visible light by a sample, either as a single wavelength or perform a scan over a range of the spectrum. The UV range changes from 190 to 400 nm and the visible spectrum from 400 to 800 nm. The technique can be used both quantitatively and qualitatively. A schematic diagram is shown. The light source, a combination of tungsten or halogen and deuterium lamps, provides the visible and near ultraviolet radiation covering. The output from the light source is focused onto the diffraction grating, which splits the incoming light into its component colors of different wavelengths. The output from the light source is focused onto the diffraction grating, which splits the incoming light into its component colors of different wavelengths, like a prism, but more efficiently. For liquids of sample held in an optical flat transparent container called a cell or cuvette, the reference cell or cuvette contains the solvent in which the sample is dissolved, and it is commonly referred to as the blank. For each wavelength, the intensity of light passing through both the reference cell and the sample cell is measured. It is then the sample has absorbed some of the light. The absorbance of the sample is related to I and I0 according to the following equation, like A is equal to log of I0 by I. The detector converts the incoming light into a current. The higher the current, the greater the intensity. The chart recorder plots the absorbance against wavelength in the UV and the stable section of the electromagnetic spectrum. Absorbance does not have any units. Absorbance does not have any units. Visible spectrum. Absorbance, one can see that the wavelength of light are absorbed and at wavelength of light are transmitted. The higher the value, the more the particular wavelength is being absorbed. The absorption peak at a value of 270 nm. It is the ultraviolet region, and so there would be a visible sign of any light being absorbed, making buta 1,3 diene colorless. The wavelength that corresponds to the highest absorption is usually referred to as the lambda max. The spectrum for the blue copper complex shows that the complementary yellow light is absorbed. The Beer-Lambert law. According to the Beer-Lambert law, the absorbance is proportional to the concentration of the substance in solution, and as a result, UV visible spectroscopy can also be used to measure the concentration of a sample. The Beer-Lambert law can be expressed in the form of the following equation, like A is equal to ED, where A is equal to absorbance and optical path length will be the next one. The dimension of the cell or cuvette, concentration of solution, molar excitation, which is a constant for the particular substance at a particular wavelength, If the absorbance of a series of sample solutions of known concentrations are measured and plotted against their corresponding concentrations, the plot of absorbance versus concentration should be linear if the Beer-Lambert law is obeyed. This graph is known as a Beer-Lambert calibration graph. If the absorbance of a series of sample solutions of known concentrations are measured and plotted against their corresponding concentrations, the plot of absorbance versus concentration would be linear. Since the absorbance for dilute solutions is directly proportional to the concentration, another very useful application of UV visible spectroscopy is studying reaction kinetics. The rate of change in the concentration of reactants or products can be determined by measuring the increase or decrease in absorbance of colored solutions with the time. Plotting absorbance against time, one can determine the orders with respect to the reactants, and hence the rate equations from which the mechanism for the reaction can be proposed. Modern application of UV spectroscopy. UV visible spectroscopy is a technique that readily allows one to determine the concentration of substances and therefore enables scientists to study the rates of reactions and determine rate equations for reactions from which a mechanism can be proposed. As such, UV spectroscopy is used extensively in teaching, research, and analytical laboratories for the quantitative analysis of all molecules that absorb ultraviolet and visible electromagnetic radiation. Other applications include the following. In clinical chemistry, UV visible spectroscopy is used extensively in the study of enzyme kinetics. Enzyme cannot be studied directly by their activity, can be studied by analyzing the speed of the reactions which they catalyze. Reagents or labels can also be attached to molecules to permit indirect detection and measurement of enzyme activity. The widest use in the field of clinical diagnosis is an indicator of tissue damage. When cells are damaged by disease, enzymes lack into the bloodstream and amount present indicates the severity of the tissue damage. The relative proportions of different enzymes can be used to diagnose disease, say of the liver, pancreas, or other organs which otherwise exhibit similar symptoms. UV visible spectroscopy is used for dissolution testing of tablets. UV visible spectroscopy is used for dissolution testing of tablets and products in the pharmaceutical industry. Dissolution is the characteristics test commonly used for the pharmaceutical industry to guide formulation, design, and control product quality. It is also the only test that measures the rate of in vitro drug release. UV visible spectroscopy is used for dissolution testing of tablets and provides products in the pharmaceutical industry. Dissolution is the characteristic test commonly used for the pharmaceutical industry to guide formulation, design, and control product quality. It is also the only test that measures the rate of in vitro drug release. As the function of time, which can reflect either reproducibility of the product manufacturing process or a limited case in vitro drug release. In the biochemical and genetic fields, UV visible spectroscopy is used in the quantification of DNA and protein enzyme activity as well as the thermal denaturation of DNA.